will comes under the will give the some and also in vibrations in the itself in the dam by the earth. Okay, the horizontal and vertical accelerations are not equal, where from the vertical accelerations and horizontal are not equal, the former being of the greater intensity, where the horizontal the vertical acceleration means uh, body weight, and the horizontal acceleration means due to the earthquake. These two are not equal, then the vibration will comes into the action. Then the initial stage of failures will be placed into the dam. That is the earthquake failures. The earthquake acceleration is usually designated as the fraction of the acceleration due to the gravity. Normally we are taking due to the acceleration due to gravity, that is g, but the due to the earthquake we are taking acceleration due to gravity is expressed as alpha into g, where alpha is the seismicity coefficient. Okay, seismic coefficient. The seismic coefficient depends on the various factors like the intensity of earthquake, that is intensity of the earthquake at the depth of the ground. Very near to the ground we are form the earthquake, it is high intensity on the dam. It is very far away from the dam, will give the less intensity. The part of the zone of the country in which the structure is located, that is categorized zones into the earthquake zones. We are India comes different zones we are located, that is in zone 1, zone 2, like that. We are considered for the what intensity of earthquakes formation by that zones we are taking a in seismic loads. Okay, the elasticity of the material of the dam and its foundation, and also we consider the material elasticity, that is elasticity property we are considering the material. Okay, which has to be adapted the design of the dam. India has been divided into a 5 seismic zones. The seismic zones we are considered, by that way we are following the seismic load. Okay, depending upon the severity of the earthquakes, that is severity means that intensity. Okay, more have intensity, they have a more chances of failures in the dam, then we consider it as a more severe conditions we are placing there, which may occur in the different places. The map showing these zones are given in Bureau of Indian Standard Code, that is in IS Indian Standards 1893 2002. Zones are given in a zone, that is part 1. The methods from the determining seismic coefficients are also described in the mentioned code. Okay, we are taking different seismic coefficients by the locating areas on the zones in the this Indian Standard Code book, that is Bureau of that is placed from the Bureau of Indian Standards. Okay, take the next. Okay. Next, the hydraulic pressure generated due to the horizontal movement of the water, because the acceleration due to the ground motion, the dam will be accelerating, and also water may be. Then the hydrodynamic pressure also generated on the dam due to that vibrations. Okay, body in the reservoir, and it consequent impairing against the dam may not be calculated by may to be calculated by this formula. Okay, the pressure will be the hydrodynamic pressure will be calculated by using this formula, that is alpha into gamma into and h into cs, where cs is calculated by below formula, that is cm by 2 into in brackets y by n and 2 minus y by n plus root over y by n into in brackets 2 minus y by n. This formula will calculate this formula using to calculate the cs, that is coefficient with various shapes of dams. The dams are generally in into the different shapes, that is in trapezoidal, or in water side will goes with the vertical face, or in angular face, that is in different phases we are considered for the construction of a dam. The shapes will accordingly we take the cs value, that is coefficients. Okay, the coefficients will be calculated by this the formula Cm by 2 into y by n, where Cm is the maximum value of Cs according to the figure, where the figure will show, where y is the depth of horizontal structure section. Okay, that is the depth of the section below the water surface in meters. Okay, where gamma is the unit weight of water. The hydrodynamic pressure we are considered, then we take the gamma value is unit weight of water, that is kilonewton per meter cube. Where H is the total water in reservoir, that is in meters. Okay, the total water pressure will be acted on the dam, where the dynamic loads that is due to earthquake will comes. Then we take the over depth of the water, that is H. Okay, the this formula will calculate, this formula will goes into will calculated the earthquake pressure, that is hydrodynamic pressure by the water. Okay, okay, next way. This formula will consider from the as per is codes. Okay, this is the effects on the crust profiles, where the crust profile is on the spillway level. We taking different failures on the dams by acting the seismicity seismicity. Okay, first diagram is unsatisfactory in areas of seismic activity. Okay, and the satisfactory other than for the extreme conditions. We safe against the what dynamic loads, that is vibrating loads. We are safely we are taking here. The last one is satisfactory with maximum inertia effect. Okay, we consider we constructed extra portions, extra construction against these dynamic loads on the from the hydrodynamic pressure. We constructed pier supporting roadway, where the roadway over the dam we are constructed, there we constructed supports also, that is in pier support roadway. These are constructed will considerably will decrease the hydrodynamic pressure against the earthquake pressures. Okay, these three diagrams will give different effects on the crust profiles. We take different structures we are accordingly by the effects. Okay, next. Okay, that's it. This is the exceptional cases on the dam. We are adding, we are acting on the dams. That is the loads of earthquakes. Earthquakes are the very unexpected loads. We are not expecting this time will come. We are considered where the zones are located. That is in India, where the zones are located. The zone will construct any dam. We take the seismicity automatically. Then we safely obstruct the loads where the seismic loads are comes into the dam by the hydrodynamic pressure. Okay, that's it. Thank you. Any doubts?
Is visible?
Yes.
Okay, proceed.
Okay, sir. Gravity dams. We already know about the gravity dams. What and in the sub in this chapter we have the topics as force acting and stability analysis of gravity dams, stress analysis, elementary profile, and design of gravity dam, other functional features of gravity dam, design theories of arch and butter dams. In this, Venkatesh already told about the force actings. We are going through this. What is gravity dams? We all are know about the already gravity dams, and once again we are going through this. Uh, it is a solid structure, and generally it is made up of concrete or masonry, and it is across the constructed across the river to create the reservoir on upstream side. These dams resist the various forces acting on it by its self-weight, and then it is known as the gravity dam. And a typical section of the solid gravity dam is shown in the figure, which is it is the upstream side and it is the downstream side, and it is the height of the hydraulic. Uh, uh, it is the upstream side height, and it is the lowest height, and it is the toy, and which is the heel, and it is the base. It is the downstream phase, and it is the upstream phase. different forces acting on the dam. In the dam, we have many forces acting, which already told by Venkatesh. Uh, the major forces are self-weight and water pressure and uplifting force, and the minor forces are earth pressure, wave pressure, and earthquake, force due to wind, and ice pressure. Now we are going to the stability analysis topic, which is the new topic for us, and mm, which means that a gravity dam may fail in the following modes because of overturning, sliding, compression, and tension. Therefore, the requirements of stability are the dam should be safe against overturning. Uh, we overcoming of stability analysis, we must be go through this safe analysis, which is safe against overturning and safe against sliding. The including stresses either tension or compression in the dam or in the foundation should not exceed the permissible values, which are like first is overturning, which is the resultant force of acting on the dam at any section passes outside the toe and dam shall rotate the overturn of the toe. The factor of safety for this is resisting moment divided by overturning moment. The permissible value in between these overturning values is 2 to 3. Sliding. Sliding is a dam may fail in the sliding at its base. Maybe it will, by water is forcefully going downstream to upstream to downside, it will cause. And in that, we should have the factor of safety is mu into sigma v by sigma h. Sigma v means vertical forces of the all vertical forces in the dam, and the horizontal forces in the dam means sigma h. Mu is the quotient of static earth pressure, and it will lies in between the value of 0.65 to 0.75. Compression or crushing. A dam may fail by the failure of its material, and the compression stress may exceed the allowed stress, and dam material may get crushed. The vertical direct stress distribution at the base is given by the equation is direct stress plus bending stress, which means stress distribution maximum or minimum is sigma v by b into 1 plus or minus 6 plus 6 into e by b. E is the eccentricity and b is the base, and sigma v is the vertical forces, whereas E is the eccentricity of resultant force from the center of the base. Tension. The masonry and concrete gravity dam are usually designed in such a way that no tension is developed anywhere, because the material cannot withstand sustainable tensile stresses. If the subjected to such stresses, these materials may crack. The tension is heavy, then material may be cracked. Crack will be formed and the dam will be collapsed. That's why we can overcome these compression and tension and sliding and overturning. It is the compression and it is the tension. Stability analysis. We are by analyzing, we will take 2D and 3D methods. Generally, we will follow in the 2D methods only. That is, let's we see. The stability analysis of the gravity dam can be approximately and easily analyzed by 2D gravity methods. Generally, we use this 2D gravity method only, and for study purpose, we can go through this. And other is 3D, which has slab analogy method and trial twist method and bi-model studies. In the gravity method analysis, the dam considered to be made up of number of cantilevers of unit width which act independently of each other. In the gravity analysis method, we consider only cantilevers only. cantilevers forces, and the will take as unit weight, and it is acting on the dam is independently. First of all, the assumptions made for this gravity stability analysis: no load are transformed to the abandon of the beam, which means it is true for that. And the foundation of the dam behave as a single unit. The whole dam will foundation of the dam whole will be unit we consider as single, and joint be in the part of joint will be perfect. And the material in the body of the dam and the foundation are isotropic and homogeneous. The material we use it for the dam, which will be isotropic and homogeneous only. The stresses developed in the dam are within the elastic limit. We will take any stress developments which are will be in a elastic limit only. These are the assumptions we made. And in the 2D analysis, we will take the stability analysis method, which is analytical method. We also called as it is geometrical method also. And the stability analysis by analytical method is done by the following steps. First of all, we consider the unit length of the dam, and then we work out the magnitude of the direction of all vertical forces. Vertical forces means which will be um, which act in the y direction, which we up, which is uplift force and other forces. For we observe the forces, and we will take the vertical forces, and then we work out the horizontal forces. Work horizontal forces, we will take all algebraic of horizontal forces, which has self weight of the dam and other few forces, and determine the lever arm of the forces about the toy, and then determine the moment of all these forces about the toy, and find the algebraic sum of these moments, which is sigma m, sigma all the moments of the dam. And then we go through the find out the location of the resultant forces of the determination of distance of the toy, which can be determined by x, and it will come by sigma m by sigma v. The moment about uh, the moment algebraic sum of the moments and algebraic sum of the vertical forces. And then we'll go about the find about the eccentric forces. Eccentric resultant is E equal to b by 2 minus x. B is the width base, and x dash is the we already distance of the toy. And next is find about the normal stresses by the expression, which is Pn, which equal to sigma v by b into 1 plus or minus 6e by b. And find out the principal and inclined stresses at the toy and the heel of the dam, and determine the factor of safety against overturning. Overturning factor safety is sigma mr by mo. Mr is the moment of resistance, and mo is the moment of overturning. And then determine also other factors of the safety. Factor of safety against sliding is mu into sigma v by sigma h. Mu we already know quotient, and sigma v and sigma h also terms we already know. Sigma v is the resultant algebraic sum of the vertical forces, and sigma h is the algebraic sum of the horizontal forces. The shear frictional factor SFF is equal to mu into sigma v plus bq divided by sigma h. Mu is the coefficient of sliding, and sigma v is the vertical forces, v is the base, and q is the shear factor, and sigma h is the horizontal forces. Sliding factor, which is always greater than 1, and SFF must be greater than 4 to 5. This is the main condition of the slide factor. and shear friction factor. Uh, if we not taken these permissible values, dam may may collapse, and certain causes will be developed in those places. The analysis be carried out for this analysis is for empty and full cases also. The reservoir is if empty, we will apply this one only. It is full, then also we apply this only. The principal stresses at the toy and the heel for the reservoir empty and full condition should not exceed the maximum allowable values. The permissible compression stresses varies from 150 to 300 Newton per centimeter square, and the tensile stresses will be 50 Newton by centimeter square. Uh, Next one is the graphical method. Actually, we did not follow this method, but for exam purpose, we'll go through this. And in this method, the entire dam section is divided into the number of gravity and horizontal section. We'll take the number of horizontal sections first of all, and at some suitable intervals only, particularly at the lace where the slope changes. For each section, the sum of the vertical forces and horizontal forces acting above a particular section are worked out, and the resultant will be drawn. For every vertical and horizontal forces, we have a resultant force that will be drawn in a graphical method, and then this is done for the each section. For we'll take a particular section and then we'll write, and again go through the next section and next section like that. And then the line joining all the points and where the individual resultant cut the individual sections is done. First we will take all for each and individual section particularly we will run the resultant sections, and then we go for each point to the cut where the point is drawn and cut at that place section will be drawn, and we will join all those lines. The line represents the resultant force and should lie within the middle third of the no tension to be developed. These all lines represent that resultant forces and also where the middle third part is lied. There is no tension will be developed in this case, and the procedure should be repeated for the reservoir full and as well as for the reservoir empty cases also. The diagram will be the graphical representation will be like will be comes. That's it. Thank you.